Hey, welcome to this tutorial on generics. I've been waiting a long time to do this tutorial, and I know that there was a lot of prerequisites to it, so I'm very excited to show you generics. And also, the playground has been crashing on me a lot. For some reason now it's importing UIKit. Hopefully it won't crash on me too much as I'm doing this tutorial. So generics, they allow you to write generic code. It sounds like a complicated word. It sounds like it's going to be very advanced, but it actually makes things more abstract. It makes reusable code that you can work with in any requirements that you define. This will allow you to write code once in a very clear and abstracted manner. Generics are so unbelievably powerful that most of Swift's entire library is built on generics. Arrays and dictionaries, they allow you to create collections that hold any type of value. Ints, strings, dogs, cats, whatever. There's no limitation to what you can store in arrays and dictionaries, and they use generics to solve that. So what problem does this solve? What are we trying to solve here? So I'm going to take this from the documentation. This is a function called swap to integers, ints. And you're going to do an in-out here, which means that we're going to do this to a variable outside of this function. So we're going to take in A and B, and we're going to let temp A, so we're just going to make a temporary variable called A, which is going to store whatever A is, and then we're going to say A is equal to B, and then after that we'll just say B is equal to temp A. Basically we're taking A and B and we're swapping them. So this function is swapping two integers using the in-out params. So now we're going to create var A is equal to 1, B is equal to 3. Notice I was able to declare two variables using the commas there, and then we can call swap to ints. Nothing abnormal here. We're going to pass it A, we're going to pass it B. And now if we see A and we see B, we see that they've been swapped. A was 1, now it's 3. B was 3, now it's 1. So swap to ints is good. It's a great little function that we wrote, but it only works with integers. What if we want to swap doubles, or we want to swap two strings? We need something more generic. If we wrote those other functions, swap two doubles and swap two strings, the function body would be the same, but the types would be different. And that would be just rewriting the same exact code. It'd be repeating yourself. That's not very dry. Generics can work with any type. So let's rewrite swap to ints to be swap to values that can take any value. So we're going to delete swap to ints, and we're going to write function swap to values. And we're going to tell it that we're going to have this variable t available. Now we don't know what t is going to be. It's going to figure out what that is later. We're going to have the same in-out, and that's going to be a variable t, which is not a real Apple UIKit variable or type. And we're going to have b as t, and then we're going to have the same let temp a equal a, and then we can just swap them. A is equal to b, and b is equal to temp a. So notice the big difference is that placeholder type t. We declare t right here as the placeholder type for any type that we might wind up using. We do this instead of declaring the actual type name. All that this says is that A and B must be the same type. What type they are is completely up to the user. So now what we can do is we can pass in any type. We can say var A is equal to cat, B is equal to dog, and now we can say swap to values, and for A we're going to pass A, and for B we're going to pass B. And now we can see A and B just like we did before, where A was cat and now it's dog, and B was dog and now it's cat. So you can name T anything you want. So we could have named this U, but it's standard to use T. If you were rewriting the dictionary, you'd need type parameters, one for key and one for value. So if you were going to make a new type of dictionary, you'd need two different types of things here, because key and value might be two different types. So you might use something like key type and value type for that, or maybe you'd use T and S and go alphabetical there, but you always use uppercase first letter. So you can also define your own generic types, not just functions. These are custom classes that you can make, structures and enumerations that can work with any type in the same way to arrays and dictionaries. So let's look at one of those generic collections that we're going to make called a stack. A stack is like an array, but it's going to be more restrictive. You can only push onto the end and pop off the top, similar to that syntax in JavaScript. A stack is a useful collection model whenever you need a strict last in, first out approach to managing a collection. So let's make a stack that only takes ints, and then we'll make it generic. And we're going to make a structure called int stack. And we're going to create items as a property, and that's going to be an array of integers. And we're just going to create a new array there. We're going to say mutating function push. It's mutating because we're going to alter the structure itself. And we're going to say items dot append, and we're going to pass in the item. And we're just going to create one more mutating function called pop. That's going to return an integer, and that's going to return items dot remove last. So that's going to pop off the last item. So we use an arrays to make a function called push that only appends onto the end, and one that's called pop, which removes the items from the array. That's great, and this will work if we use it, but let's make it work with more than just integers. Let's make it generic. So we have this int stack, and instead of int stack, let's just call it stack, and let's pass in t. We're going to use t as the generic variable. And this time, instead of ints, it's going to be an array of t's, whatever t is. And then the mutating function item is not going to take integers, but it's going to take that t. And the mutating function pop is not going to return integers, but it's going to return t. So this is a generic. The difference is that t is a placeholder for the type that you would use in the end, whether it's an integer, a string, whatever it is. We replace the type inference with t instead, so that when we declare a variable of ints, we replace it with a variable of t's. So let's use that stack and make a stack of strings. So we can say var string stack is equal to stack, and then we just have to tell it what type we're passing in here. And that's going to be a stack of strings. So what we've done here is we've created a new stack, which is just like an array, because what we've created up here is an array, which has items, which you can push and pop and all that stuff. So now we can say string stack dot push, and we need to pass in a string, so we'll pass in a cat, and we can pass in a dog and a rabbit. Now, if we were to trace string stack, you could see that it has cat, dog, rabbit, and we could do string stack dot pop, and that will push off the last one and it will return it, which is rabbit. And then we could trace string stack again, and now we just have cat and dog. For example, if we wanted to create a function called find index, we're going to tell this that not just that it should be t that we're going to pass in, but that t should be conforming to the protocol equatable. And I'm going to tell you what equatable is in a second, or equatable. That is going to be passed in an array, which is going to be of type t, and that t must be of type equatable, and the value to find must be of type t as well. And that whole thing is going to return an integer, but it's got to return an integer optional because we may or may not find anything when we look for it. So we're going to loop through this array, but we're going to also grab the index. Remember this? So we're going to get the index and the value, and the way we loop through things by getting the index is we use this global function called enumerate, and we pass in the array. And then all we're going to say is if value equals value to find, then we can return the index. And then at the end, we're just going to return nil. Because if it gets to this point, it means it didn't find anything. Because it's going to loop through this entire loop. If at some point it returns the index, well, then everything's going to stop. It's never going to get to nil. But if it does get all the way through the loop, then we know we haven't found anything. We have to return nil. So now we can use this find index with an array of strings or ints or whatever we want. The only requirement is that whatever type we use has to conform to that equatable protocol. Now the Swift standard library defines a protocol called equatable. It requires that any conforming type implement the equal operator and the non-equal operator. So that's the double equal sign and the non-equal sign. That's the way to compare any two values to see if they're equal or not equal. All of Swift's standard libraries automatically support the equatable protocol, so you don't have to worry about that. But if you were to create maybe that dog class, you may not be able to say, is dog equal to dog or something like that. Not everything is equatable. That's why you have to make sure that something conforms to the Equatable Protocol, that you can be sure that if you call it equals equals, it's not going to throw an error. So now we can say let double index equal to find index, and we got to pass in an array here. So we'll pass in 3.14159, and we'll pass in 0.1, and we'll pass in 0.25, and we'll try and find 9.3 in there. And you can see that it returned nil. Well, index is going to be an optional integer because that's what this find index returns. We don't need to type it as that. It's going to do that automatically. So we're passing in doubles, and it's going to return an integer. So now we can do this again, and we can do this with just strings. So we can say let string index equal find index, and it's got to be an array of strings here that we want to pass in. It doesn't have to be, but we're going to do that. We're going to pass in Mike, Malcolm, and Andrea, or Andrea. And we're going to look for Andrea. And you can see that it returned 2. And that sum there, you can tell that it's returning an optional. If we did this, you can see it's going to return the raw value because we are forcing the optional if we use the exclamation point. So that allows us to use find index with any type at all, as long as it's equatable, whether it's doubles, ints, strings, whatever. So sometimes we want to define a protocol with specific methods that the user says they need to be called in specific properties, but we don't want to demand that the user of that protocol have to be forced to use specific types like strings or ints for those properties. We want them to be able to use whatever they want. So let's say that we want Thid to provide a container for any class that can be a container of anything. Can be a container of structs, can be a container of ints, strings, whatever. So we create what's called a type alias, and that will say that the type of whatever it is can be declared at the user's discretion. We'll create this protocol here that's going to use the type alias, and we'll call it container. And this will be a generic container. And we'll write this type alias. That keyword type alias means use item type for now, and when they define the class, they will say item type is equal to string or item type is equal to integer. So we'll declare item type as a type alias. Then we'll say mutating function append, and we'll say item is of type item type. So when they're going to append items of type item type, which is whatever they declare. Then we're going to create a count. So var count is of type integer, and that's only going to be a getter. Now I didn't show you how to declare just a getter yet, but I'll show you in a second. Then we're going to tell them they need to declare a subscript, which needs to take in an integer, obviously, because we're going to grab in the square brackets the item, and then it needs to return whatever that item type they decide to define. And that's going to be a getter as well. So we have a container that appends items and gets those items back, and we also have a count. And what those items are that we append, we don't define. We leave this up to the user to define. So this protocol doesn't specify how the items should be stored or what type they're allowed to be. To achieve this, the container protocol declares that associated type called item type, written as type alias item type. The protocol doesn't define what the item type is an alias for. That information is left for any conforming type to provide. So here's an implementation using the string container, otherwise known as the string stack. So we're going to create a struct called string stack, and it's going to implement that container. So now we're going to create some items. We're going to say that that's equal to a new array of strings. We're still going to get an error because we haven't implemented everything yet. We're going to write our mutating function push, which is not declared in the container, similar to the int stack or the string stack that we used before. I can't remember which one it was. Then we're going to do item is of type string. All we have to do is we have to say items.append, and we're going to append that new item. So that's just going to take the item and append it, which is going to put it on last into the items array of strings. So then we can call mutating function pop, and that's going to return the string that we decide to pop off or remove. And all we have to do is we have to return items.remove last. And what that does is it removes the last item, And remove last returns whatever it removes. So it's going to return what it removes and remove the last item at the same time. We need to use this type alias, and we need to say that that type alias, which is of type item type, is this time going to be equal to a string because we're doing the string stack. And then we're going to write mutating function append, and that's going to be an item of type string. And we're going to append the item by using our own self.push method from up here. So we're using our own method called self.push, and we're going to push in that item. Now we're going to create that getter count property. And how do we declare it as just a getter? Well, this is a shorthand, and it's actually really convenient here. So we just say var count is equal to an integer. And all we have to do is use these curly braces, return items.count. So this looks sort of like a closure, but it's not because we're not using the equal sign. Notice that we don't have anything between this and this, and all we're doing is returning this. So that's the shorthand for just the getter. That count cannot be set. And then we have to declare our subscript, which is going to take an I integer, and that's going to return the string. And that's going to return items I. So that's going to get the item at I and allow us to access it using the square bracket notation. So that's great. We have a string stack. We could create a new string stack, and we'll just call it sStack. And it will be equal to a string stack. And it wants the items. So we're going to pass in an array of strings. Hi. There. And now because we're using the subscript, we can say get item at 0, and it will return back hi. And we can say sStack.count, and that will return back the count, which is 2, which is a read-only property. And you'll notice that if we try and set that as 5, it's going to throw an error and say that cannot assign count in stack. So it's a read-only property. It's not allowing us to set that. So we have our string stack, and this works great, but we don't need to declare the type alias at all in here when we're implementing this. We can actually comment that out and everything will still work. And the reason is because you always hear about Swift inferring different types. And again, Swift, by looking at this class, is smart enough to know that item type is going to be equal to a string, because anywhere that we used item type in the protocol, we replaced it with a string. Therefore, it must be a string. So you can leave the item type out and Swift will be able to infer it. But it's good to just write it in to show you that that is what the type alias is doing. We are setting a type alias. And now we are still setting a type alias, but Swift is automatically figuring out what that type alias is, even though we're not writing it. You could also rewrite this entire struct to be completely generic. So let's do that. So instead of calling this string stack, let's just call it stack, which we did before. We're going to tell it that everything in here is going to be of type T. And we don't know what type T is going to be yet, because that's going to be up to the user. Now, items is not going to be of type string, it's going to be of type T. And when we push, the item that we're going to push in is not going to be of type string, it's going to be of type T. And when we go to pop, the thing that we're going to remove is not going to be of type string, it's going to be of type T. And when we go to append, the item that we append is not going to be of type string, it's going to be of type T. And when we go to grab the subscript, we're not going to grab the subscript of type string, we're going to grab subscript of type T. So now we've created a generic stack here, and we could use this for ints this time if we want. So we could say var instack is equal to a new stack, and we have to declare that it is of type int. So now we can create some ints for our instack by saying instack.append, and that's going to be a 1, and we can append a 2, and we can say instack.count, and that's going to be 2 items, and we can say instack.one, and that's going to return the item at index 1, which is a 2. We could rewrite this entire thing. Instead of being an instack this time, we could say var string stack again to be equal to a new stack that's going to take only strings. And if we try to push in an int, it's not going to work, because it says cannot convert the expression's type to type string. It knows it needs to be a string because the generic up here, this part right here, is saying that we are pushing in a string, which you can see we filled in right here with a string. So we can append a 1 this time. We can just trace string stack. And you can see that it's just a stack of 1. So the last thing I want to talk about is the where clause. It can be useful to define requirements for associated types, and you can do this by defining where clauses as a part of the type parameter list. A where clause enables you to require that an associated type conforms to a certain protocol and or that certain type parameters and associated types to be the same. So you can use this where clause to kind of query things by placing the where keyword immediately after the list of the type parameters, followed by one or more constants for associated types, and one or more equality relationships between the types and the associated types. So let's take a look at what this would look like. So we have our container here, which is the protocol for the container, and we can create a function that takes only containers, and we'll say that all items match. And I got this from the documentation, and we're going to tell it what sort of protocols this needs to take in. And like I said, you don't have to write T here, you can write anything you want. And in this case, we're going to define multiple protocols it must match to. We're going to say it has to be C1, C2, and we want to say that C1 must be a protocol of container, and that C2 must also be a protocol of type container. Now, what we also want to say is that C1 and C2 where C1 dot item type, because the container declares an item type, is equal to C2 dot item type. So this is going to make sure that whatever it is that we're adding into the array or the stack, if that stack is going to be a string stack or an int stack, that they both have to have the same types in their stack. Like they both have to be string stacks, or they both have to be int stacks, or they both have to be double stacks. And that's what this where clause is doing. It's saying C1.itemType is equal to C2.itemType. They both must have the same stuff in them. And there's another thing that we have to declare, and that is that where C1.itemType must be equatable. Equatable. So now we're saying that C1 item type, whatever we're pushing into the stack, has to be equatable, meaning that we have to be able to use the double equal sign or the non-equal sign to compare things. So we can put this where on a new line, and we can also put this C1 on a new line, and then we can put this next part. This is the parameters of the function, although it looks a little funky because we're all the way down here. We can say some container is going to be of type C1, and this is generic here. We don't know what C1 is going to be. All we know that is C1's item type and C2's item type must be the same, and C1's item type must be equatable, which means that C2 item type must be equatable as well because C1 and C2 are equal. So some container C1, and we're going to make another container which is going to be of type C2, and this whole thing is going to return a Boolean. And this is going to tell us that all items in these two things must match. So we're going to check that both containers contain the same number of items, because that's important to see if they match. So we just say some container dot count, because we know that in our protocol we have a count property available, and it's just a getter. We have to make sure that that's not equal to another container dot count. If they're not equal, the two counts are not equal, then we're going to return false and say that no, all items do not match in these two containers because maybe one has one more than the other. And then we're going to have a situation where we're going to check each pair of items to see if they are equivalent. So what we're going to do here is we're going to loop through everything. We're going to say for I in 0 to some container dot count. So we're using the range here to get I and loop through the entire container by using the range. So this is our sort of for I in this is less than that I plus plus sort of thing, except it's easier because we can just use the range, and we're using that count property. So we can say if some container I is not equal to another container I, then we have to return false. And then at the end of the entire for loop, if we got through the entire for loop, that means that all items matched, so we can return true. So in this case, C1 and C2 must adopt the container protocol, which we defined above. And the item type, the contents of their container, they must match. And C1 must adopt the Equatable Protocol. And by definition, that means that C2 must have the Equatable Protocol as well, because C1 and C2's item type must be equal. So then we check both containers to see that they contain the same number of items, and then we loop through all the items and check that the items match completely. If they don't match, then we return false right here, because that's going to mean that it maybe has one more item than the other one. And then we loop through all the items and check each item to see that the items match completely. If they don't match, then we return false. So let's actually try this out here and see if this works. Let's grab our old friend, the string stack. Just do a little trick here. We're going to do an undo Z here until we get back to our struct, and all we're going to do is we're going to copy it, and then we're going to redo everything. Now that it's in the clipboard, we can kind of use it. So there's our stack, and we can use this as a string struct. So we'll say var bunch of strings is equal to a new stack of type string, and then we'll say bunch of strings dot append, and we'll append hi, and then we'll also append there, and we'll also append friend, and then we'll create another string stack, and we'll call this bunch of strings 2, and we'll say that items is going to be a string of hi, there, and we're using the initializer here that automatically comes with structs, friends. So now these are not exactly the same. So we'll test this out and we'll say all items match. And this must be some container. It has to be a container, which it is. So we say bunch of strings and bunch of strings 2. And we'll see that they do not match. Now if we change this from friends to friend, then we'll see that these do in fact match. So to finish off here, you can only imagine that that's how Apple was able to write their arrays and dictionaries, because they had subscripts to provide us with the square bracket notation directly from the class itself. They had generics, which allowed us to implement any type in the array or the dictionary. And then they had protocols like Equatable that would allow them to make sure that items could be compared. So if you're going to need to compare two items, you want to make sure that it conforms to the Equatable protocol. And then you have some extremely powerful stuff when you use that where clause to make sure when you're implementing multiple protocols at once that those two protocols match in some way, or they don't match in some way. You can make sure that they conform exactly like you want them to conform. So that's pretty darn powerful stuff here. And you can create your own types that other people could use. Well, I hope that your mind is thoroughly blown. I know that my mind exploded the first time that I read this and tried to implement it. We'll see you next time. Please subscribe to us on YouTube, Twitter, Facebook, Google+, and whatever else there is to subscribe to us on.